Hi everyone, thank you very much for that intro. Yes, hi, I'm Dave, I work for Underscore and I write books. There's a free one, go and get it. It will help you understand the rest of this talk. Without it, you might be lost. So I'm normally talking about Scala, and I'm expecting you're expecting me to talk about Scala, but I'm going to do something slightly mad today, something slightly ill-advised. I'm going to talk to you about building our own programming language to operate on top of Scala. We're going to build a little scripting language together. Now, why would I be interested in doing that? Well, to motivate this, I have a side project that I work on. It's like a sort of non-profit kind of thing. It's a data collection platform for environmental groups. So it's for people going out into the field and measuring water quality or collecting litter or looking at animal behavior. And they want to pull all these data sets together and throw them into a centralized store, and then we have this sort of data pipeline which does maps and charts and exports and fun things like this. Now, the key thing about a cartographer is that users can design the kinds of data they want to collect, a bit like SurveyMonkey. You can kind of put a few fields together, you can design a data type, and we need to be able to operate on all these heterogeneous data types without knowing what they are at compile time. So we need some kind of representation of code to run on these things that may or may not be Scala, and there are arguments as to why it shouldn't be Scala. And it's to do little things, just little bits of glue code, form validation, how we make a marker on the map, just tiny little things. So we've got a number of choices, right, of how to implement this. The first one is we can just say, okay, we're going to build a really simple system, no clever expression languages or anything, and we'll limit users' options. But clearly that's boring. Then we could say, okay, well, what if we invent a little DSL to represent the kinds of operations people want to perform on these structures, and then we can build that with that in Scala, or maybe we can build it from a user interface, or maybe even expose a little DSL. Well, I started down this path, and very quickly I needed functions, and then I needed variables, and everything went crazy. And then I thought, well, maybe I should embed a scripting language, right? I mean, other people have done this in the past, and it's never been a bad idea. We've never produced any bad software from that. So maybe I can embed like Python or JavaScript or something, or Clojure or something in. And I thought, no, those aren't invented here. What we need to do is make our own scripting language. As a startup, we clearly need to make ill-advised technical decisions and live with them for years to come. So I've done that. This is a very early prototype project. It's more of a toy than anything. Don't use it. It's not a real programming language yet. But what's interesting is the journey to make this language. And I think it exposes some patterns which we use in functional programming. So I want to talk to you not about using this little language I've made, but how we can build our own languages on top of Scala. So I'll talk a bit about that, and then I'll talk a bit about why it's a bad idea to do this at the end. Okay, so let's look at some requirements first. Right? The main requirement for this language is I want it to be serializable. So users are going to design data, those definitions, those schemas go into a database, and if we're going to have fragments of custom code, we need them to go into the database alongside the schemas. And that precludes a lot of Scala, because when we do functional programming, we typically wrap up functions. Functions are not serializable unless we're using some clever technology. And so we want a language which is sort of restrictive enough or dialed back enough that we can actually serialize it. But we want it to be able to operate with Scala. We want to expose parts of the platform to these scripts and use them within the scripts. We may do something really dumb, like making these exposed functions call out to a database or call a web service, so we may want to make them asynchronous. And because people that are not necessarily expert Scala developers are going to be tweaking these scripts, we want to protect against infinite loops, running out of memory, stack overflows, all sorts of stuff. And I've put type checked at the bottom there. I'm really interested in investigating adding types to this kind of thing, but I've realized that this is a big thing, and I'm a small person. So I haven't got there yet. So let's create the language, okay? Right, we need three things to make a scripting language. The first is a representation of the programs we want to run. This is like an abstract syntax tree or an expression tree or something like that. That's critical. And we need this thing to be serializable, either in source code form or in tree form. And then we need an interpreter. An interpreter is just a function. It takes in a tree as input and it returns a result, the thing we want to compute. But we're also going to have to deal with complexities like asynchronousness and error handling and things like this. So typically what we'll do in Scala is we'll wrap that result in some kind of monad, okay, or some kind of wrapper. So our interpreter is this function, and then the third thing we need is some nice syntax, so some way that we don't actually have to define nested case classes to represent our programs. Now, this syntax could either be a Scala DSL, or it could be a fully fledged parser using a parser combinator library. You can plug in what you want. I'm not going to talk about that. I'm using FastParse for Atlas, which I highly recommend, but we can use anything on this end, and it's a separate talk. Over that end, though, is the design of the interpreter, and I think that's what's interesting to talk about. So, I'll show you a complete example of what we're going to build, and then we'll build it in stages. So this is the language. This is a little fragment of Atlas code. It's dynamically typed, functional, statically bound, lexically scoped, easily evaluated programming language. Okay, so we have things that we know, like we have variable definitions, we have first-class functions, we have like little operators, and we can call functions, this kind of stuff, okay? When that is all run through the parser, we get out a big old abstract syntax tree. Don't worry about the details. We're going to cut this down and rebuild it from the ground up, okay? So we're going to be taking something like that thing on the right and running it through an interpreter. So an interpreter is something that takes in an expression and returns a value. Well, one thing we haven't discussed is what is a value. So in addition to building our abstract syntax tree, we also need like a runtime. And so for the sake of this talk, we'll just say a value is an integer or a Boolean. But we can add whatever data types we want. We don't have a type system in our language, so it's easy to add new data types. Okay. So let's pick out a small subset of the language and work out how we would model it. Let's look at expressions. No variables, no functions, single lines, this kind of thing. For our abstract syntax tree, we're going to need, well, very little actually. We just need a data type, we'll call it expression, and we'll have expressions are either literals, which wrap up a value, an int or a Boolean, or they're infix operators, which will just directly represent what we want to show in the equations. So the infix operators will have an expression on the left, an expression on the right, so we can sort of nest them. I'm representing the operator as just a string. That's not necessarily a good design point, but it makes the slides look nice. So you can use an enumeration or something like this, that's fine. So with this data type, here we go. We have an expression tree to represent our expressions. Yes, that works. But the interesting thing about this is we can also represent incorrect expressions. We can actually validly represent programs that probably, well, may or may not run, depending upon what semantics we want to ascribe. So this is a sort of an interesting point here. If we were building a regular Scala library, we would probably be uncomfortable with this kind of type error. And we might solve this by adding a type parameter to expression and using Scala's type system to correctly compose expressions. And if we go down that route, you get into good old functional programming, composing functions, free structures, free monads and all this kind of stuff, and it's possible to go very, very far. But that's a different talk. What we're going to do in this one is, if we go down that route, we start to use Scala functions, and we can't do that for this serializable case. I'm going to go in a different route. We're going to deal with type errors at runtime. This is what would happen in a dynamically typed scripting language. So we'll say our interpreter returns an either. The error on the either is just a case class. And with that, we can write an interpreter, okay? And this is pretty straightforward, I hope. So we have an eval method. We take in the expression, return the either. And then when we see a literal, we're just doing a little bit to wrap that in a right. And then when we do anything like a non-terminal, we're traversing, we're going to have recursive calls in there. So to do a plus, we evaluate the left and right, and these return eithers. So we pull the values out. And we want to add the values together down here, but we need integers to do that. So we'll have some hidden little step here that will decode a value into an integer, and this will use probably a type class, a decoder type class. I'm not going to show you the implementation of this, but this thing can return an either. So it'll either decode that as an integer or basically raise a type error. So this is what's giving us our type errors. And with this sort of model, we can do a whole lot, right? We can get a quite sophisticated expression language. So we can have built-in operators, built-in functions, we can do certain types of control flow like if, and we're just piggybacking the things in our language on top of the same representations in Scala. We can also do things like collect different types of errors, and we can spot them at runtime. So we can actually have maybe a slightly less tolerant runtime than Scala's runtime. So you take two doubles and divide one by the other, you get a weird number. We could prohibit that, you know. So, but there's a kind of a problem we've hit now. I said before I want to be able to make our language asynchronous. I want to be able to adapt it to different scenarios, and we've just hard-coded an either into this. So let's get rid of that. Let's generalize this result type of this interpreter. And this is our existing interpreter. I'm going to tweak a little thing, and where's my cursor? Watch what happens here. Boom, that becomes an F. So we're going to say now, our interpreter is going to be an interpreter that returns Fs of values. And F is some container. What kind of container? Well, it's any monad where we can raise an error. So we're pulling in a type class to restrain that from cats or Scala Z, and that type class allows us through implicit methods, through extension methods, to map and flat map, to call this pure here. You see I had right written there before. Pure is just another way of saying here's a success. And then there's another method which you can't see called raise error, which is the equivalent of creating a left. So it will, you just specify a runtime error, you make the instance the case class, calls raise error, that turns it into a left and will fall through in the computation. And this is great. This gives us the ability to create interpreters for different scenarios. Here's a synchronous interpreter. I built it on top of either, and I call eval and I get an either back. But I can use a couple of more little bits here. I can make an asynchronous interpreter where I mean, if you know either T, you know it, and if you don't worry about it, but this is basically having a feature of an either and running that through the interpreter as well. And when I call that back, I get a feature. So we can now do a whole bunch more stuff with this. We can run our programs synchronously or asynchronously. We can turn them into Monix tasks or Twitter features and integrate with whatever platform we have. And the best thing about this is the actual script we're running is oblivious to this. If somebody writes, call database, get result, add 1, they just write it as call database, open brackets, close brackets, add 1. They don't look at features and they don't chain on things. It's the interpreter that deals with the complexity. So we can make the scripting language simple, but make the implementation very flexible. So the next thing we want to work on is our interpreter at the moment is stateless. And that prohibits us using variables. If we can't use variables, then we eliminate for loops and things like this. So there's a lot more things that we need some state for. So let's look at adding some state into our interpreter. So we're going to build a new type of program now. We're going to actually be able to have multiple lines, and we're going to be able to have variable definitions. So we need kind of 3 new forms for this. We need something to represent variable definitions. I'm using this let keyword here. We need something to reference a variable. So wherever I write the name of a variable in an expression, I need something to represent looking up the value of that variable in the definitions that we've made so far. And then for a third thing, we need something to allow us to make programs that have multiple lines. So I'm going to borrow the concept of a block for this, just the same as a Scala block, and this is what they look like. So I'll go through them. A reference just has a name in it. Which variable are you looking up? A let expression just says, here's a name, and here's the right-hand side of the equals, right? There's an expression on the right-hand side. And a block is 0 or more expressions. I haven't included a statement, but you would normally do that, but we'll just simplify it here. Some expressions in statement position and 1 expression in return position. So we're modeling let as an expression. We're going to say, all right, well, this is going to evaluate to some nonsense value like unit or null or something, but as a side effect, it's going to bind our variable. And if we had a first-class representation of a statement, we could skip this little dance. So these guys are both in statement position. We evaluate them, we throw away the results. Well, they don't have any results, so we don't care. And then we get to the last one, and that's our result of our whole program. Okay, so this part's easy. How do we deal with this in the interpreter? Well, the interpreter at the moment is just returning this F, right? And this is how we're doing error handling, so an either or whatever. But the problem we have is that the interpreter only takes an expression as input. Now imagine we're evaluating one of those references, a variable reference. We're evaluating the reference x. Well, the result of that could be anything based upon what the last assignment to x was in our program. So what we need is to pass into our interpreter a set of assignments. And we normally call this, I'm going to call this an environment. And you'll see this in some literature around this kind of thing. So an environment is basically a set of variable bindings. We could do something clever like a scope chain. That would be more advanced. In this talk, we'll just have what is a variable name and what's its current value, okay? So we pass in an environment and then pass in an expression. If the expression references a variable, we can just go into this map and find out what the current value is. That's half the story. There's another half the story, though, because some of our expressions can change the environment. And this is a pure functional interpreter. We don't have any mutation. So we're going to have the ability to change the environment by returning it. So most of the time, we'll be evaluating an expression, we'll have an environment, and we will leave it unchanged, and we'll just return it. And when we're evaluating a let expression, we will add a new binding, a new variable name to that environment, and we will return that with the extended to include the variable. So this here now is a complete definition for our interpreter. We can go away and code this. We'd have 2 arguments, we'd have a bunch of tuples, we'd have to constantly be tupling things and untupling them. And we can get around that, though, with a nice little bit of a kit from our functional programming library, from another data structure. And the way we do it is, first of all, I'm going to change the arguments here. I'm just going to flip them. So now we're saying an interpreter is something that goes from an expression to a function where I can feed in an initial environment with some initial variable bindings, maybe something that I feed in right at the beginning of the program, or maybe something that has come from the previous expression we evaluated. And then that function there will take that environment and transform it and compute a value. Okay? So you can imagine we feed in an expression at the beginning, and the result is this giant function that does all these steps, and every step threads the environment to the next step. And there's a name for that. We can use a special monad to represent that, and that's the state monad. Who's used the state monad before? Okay, good. So it's about half of you for the camera. So I'm not actually going to describe you how to use the state monad because I don't have enough time. But I'm actually using a monad transformer here. So this type here, for all intents and purposes, is the same as taking an F and wrapping it in something that can change the state. And we can still do all the same things we can do with F. We can map, we can flat map, we can call this pure, we can call raise error. That all works as well. And then we just have a couple more methods that come from the companion object on state T. One which lets us get the current environment, so we can pull it out and look at a variable, and one that lets us change the environment with a function. So our interpreter, which looks a little bit, I've added code, but really it's the same kind of thing. This code here is just the code we wrote before. I wouldn't have had to change anything if I had enough space on the slide. It would just work exactly the same. Pure, raise error, flat map. And what I've done, though, is I've added a type alias, which I don't think I use anywhere in the rest of the talk. I meant to take it out. But I've said, this is now internal to my interpreter. I've got this step, which is my state T. This is the thing which is passing along the variable bindings. And when a user calls this, they're just going to call this method, and they're going to say, here's my expression, here's my environment, now get me back an F. And all the environment stuff happens internally. So we can still work on any F, and we can piggyback, we can add this environment transform on top. So how do we implement the rest of this? Well, block expressions, they're not actually using state T at all. We're just going through the initial expressions, calculating all the results, getting a list of all the results and throwing it away because we don't need them, and then evaluating the last expression. And for refs and lets, I'm not going to show you the code, but it's a one-line implementation in each case. we'll just look up the value in that map, and we will, for the let, we will evaluate the expression and then flat map and set the value in our environment. So again, these are one-liners, but they're long enough that I didn't want to include them on the slide. And what this gives us is variables in our programming language, which gives us an enormous amount of flexibility. We have a flat namespace. It's a really simple variable system with our map, but we can easily extend this to have scopes and blocks and the sort of scoping semantics we expect from Scala. And we can do some checks on our variable definitions as well. But this technique actually applies in a wider context, because now, oops, oh, there you go, that was spoilers. Now we have interpreter state, right? And that doesn't have to just be variable definitions. We said earlier we didn't want infinite loops, and the way you stop an infinite loop is you just measure the time and cut off after 200 milliseconds or something. So we can actually have state inside our interpreter to track evaluation and to cut off user scripts if they use too much memory, they run too long, or they do things they're not allowed to. And that technique, I've got a really simple implementation of that technique, a naive implementation in Atlas. Okay, so we've got most of the way there, but we're missing one critical part of our functional programming language. And so let's look at implementing functions. So when I teach Scala training courses, by the way, I also teach Scala training courses. Come talk to me if you want Scala training. Just because John did it, I can do it as well. When I teach Scala to imperative programmers, I always ask them, what is a function, right? And I want them to say, a function is what's the thing that makes a function different from a method? It's a value. A function is a value. Yes, absolutely. That's the answer I'm trying to get them to give, and then we talk about composing functions. And this is fine for us functional programmers thinking about functional programming, but for implementing an interpreter, we need to make a subtle distinction. A function is actually an expression that we write, and the value is a little bit different, and I'm calling it a closure. And the difference between a function and a closure is, this is the function, here it is, but the closure is capturing both the function and the state that we're closing over. So when I evaluate the definition of a function, I need to say, what variables are in scope right now, and does that function relate to any of them? And if it does, I have to store the current values alongside the function definition, and later on, when I come to call the function, they're there ready, yeah? So, I don't know, I suddenly realized, oh my God, that's what closure means. That's the difference between a function and a closure, is this subtle difference. So, in order to extend our expressions, we need one type of expression to define a function, and it's just the names of the arguments and an expression for the body. That's simple. And then we need an expression to represent applying a function to arguments. So here, the function is an expression. So here we're looking up the values stored in our environment. It's an expression, but we could have a function literal here, and we have a list of expressions as our arguments. And then on the value side, we also need a new value. So our values are now integer or Boolean or a closure. And a closure is just a function and an environment, the same thing we're using internally with an interpreter. So I'm going to do this part in pseudocode. I'm not going to show the full implementation, but this is almost line for line what you would write. So how do we deal with a function expression? Well, all we do is we grab the current environment and we wrap the function in a closure with the environment. It's really, really simple. And how do we deal with an application? Well, that's a bit more involved, but this is like line for line what you would do. So first of all, you go to this expression here and you evaluate it, and you hope it's a closure. And if it's not, you're trying to call an integer or something, and that's a runtime error. And then, when we have a closure, we have the environment that was stored when we compiled the function definition. So we can just store the current environment and set the environment to be whatever was stored in the function. Then we can evaluate the function body. By setting the environment, we're kind of changing our scope, so we have all the original variable definitions in. So we can bind the parameters, evaluate the function body, and then just before we return, we swap back to the original environment, which moves us back from where we defined the function to where we're calling it. And there we go. That's line for line, one line of comment to one line of Scala code. That is how we'd implement that. And that gives us functions. I've made a bunch of design decisions here, by the way. This is lexically scoped, it's statically bound, and so on and so on. And this is just mirroring the semantics I'm used to from Scala. But I guess if you're a programming language enthusiast, there are many design decisions you could make here about how to implement these things. So we've got a fully fledged little functional programming language now. But the one thing we're lacking is a standard library. Okay? So on its own, we would have to do a lot of work to implement all of the stuff ourselves. So we're going to fix that by allowing our programming language to call out to Scala code. So we'll add one final thing, which is the concept of a native function, which I really like. And I'm going to do what John did here, and I'm just going to show you that this is a nightmare and just move past. So what we need to do this is we need to add a new type of value. Now remember I said I wanted the programs to be serializable at the beginning. That means the expressions need to be serializable. I don't care about the values. Because then I can have a program and load it from the database, and I can pass some initial values in my environment, right? And if I define my initial values using this, I can publish Scala functions into my namespace in my script. So this is just wrapping up a Scala function. Actually, it's more complicated than this because we might be operating in some arbitrary monad, and these native functions need to respect that monad. So we actually have to return a statesy of an f. Okay? And now we've introduced a type parameter here, and that means that it will travel all the way up this value algebraic data type, and that means our environment is now parameterized, and a whole bunch of machinery is now kind of bound to the interpreter. If the interpreter is returning a future, these things have to take that into account. And so that's a little bit of a downside, like we have more stuff is being sort of tied to the interpreter in a way. And we need other machinery as well. I'm just going to list what this is. So writing functions in Scala returning this kind of thing is hard. So we'll have some nice syntax. We can make some DSLs to sort that out, and you could use shapeless. I've actually just used SBT boilerplate to do this here. And then this is an interesting thing. Remember back when we added two values together, we decoded them to integers? So we need to have a type class to go back and forth between values in our program and Scala data types. Well, functions are now values, so we now need encoders and decoders for functions. And that stuff is a little bit crazy as well. So we have ways to turn closures and natives into Scala functions that I can call from Scala, and ways to turn Scala functions into natives that I can call from the script. And there's, you can see the source code for that. It's not for the faint-hearted. And then we're done. So we have a complete environment, and that is more or less like a programming language we can embed in Scala and we can use. So I'll wrap up. The features of the language, all of this stuff, are actually not that important. I'm not really interested in getting you to use Atlas. Like, that's not the goal here. Well, what I wanted to do is take this sort of interpreter pattern that we've talked about many times before and actually produce something that we can recognize as a scripting language. What do we need to build code like what we use every day? And we've seen that, and we've seen a bunch of cool functional programming stuff. So we've seen how we can generalize over monads, and thus we can integrate tightly with different libraries. We've seen the different steps we need. There's different extra functionality we need to add to the interpreter to cope with different constructs. And I think there's a really interesting sort of like another talk in what is the space of design goals for here. I guess the next step would be to add some type checking, which would just be another interpreter. You interpret to a type rather than interpreting to a value. Okay, so I wanted to finish up. Why is all of this a terrible idea? Well, if you go back to my cartographer, the platform at the beginning, first of all, this language is immature. We're missing IDEs, we're missing debuggers, we're missing all of this stuff that we rely on as Scala developers. So that's terrible. We should never use that. This is unfamiliar. If we got a user to program in this, they'd say, why can't I program in JavaScript? Well, we could maybe have a conversation about that, but we wouldn't necessarily convince them. I've got some benchmarks. This is about 2 to 3, maybe 4 orders of magnitude slower than Scala. It's using a stack of about 3 monad transformers, and I don't know if you've listened to this podcast really with John DeGoes. They talk about how the performance problems of monad transformers. I mean, the implementation could easily be optimized, but in its naive state, it's quite slow. It's 10 times slower than running JavaScript in an interpreter on the JVM, so that's not too bad. And other options are available, right? So there's all these ways of embedding scripting languages into Scala. I'm including Clojure as a scripting language simply because you can serialize it and run the compiler very quickly inside the JVM. But finally, there's one really good reason, which is this sort of principle of least power, i.e. the less power you give to your users or to the computations within your platform, the more flexibility you have in the design of the platform. And here we're giving a fully fledged programming language, putting it inside, which means that we start having to deal with all of these possibilities of what might happen, and we're very restricted in our design. And sometimes the results of that might not be what you really expect or what you really want. So thank you very much. You can see the code, the book, the slides. Thanks for listening.